Okay, last session we discussed about the how my Mossbauer spectroscopy is been recorded. So Mossbauer spectroscopy. Okay, so we talked about how my what are the isotopes actually responsible for the activity of Mossbauer spectroscopy. What is the energy gap which is required to match my uh, energy required to produce the gamma ray to excite my ground state nuclei to excited state, and then we need some isotope where my iron, generally we are looking for the majority of the nucleus is the iron center. Iron center we are looking for, and that iron actually uh, real iron active. Iron 57 is the active isotopes for the Mossbauer spectroscopy. And then iron 57, how we can make that energy gap to produce that gamma, that amount of gamma ray which is actually active, required to absorb my gamma ray. For the iron 57, another iron 57 excited 57 which is required, which is comes from another source, that is iron 57 5 by 2 isotopes of 5 by 2 excited state, and that is actually come from the cobalt 57, and that cobalt 57 comes from the bombardment of the neutron to iron 56, and then it produces cobalt 57, that is the radioactive cobalt 57. That cobalt 57, so we discuss about that my iron 50 gamma ray. Oops, sorry, this produce gamma ray require ray actually comes from my cobalt 57 isotope. Okay, and that cobalt 57 actually radioactive, which is actually radioactive. Radioactive. How we can produce this cobalt 57 actually comes from the iron 56 26 plus we are actually bombarding by a deuterium atom. This one, two. Sorry, initially I said it is a neutron, not the neutron. This is deuterium atom, high speed, high energetic deuterium. It actually produced the cobalt 57, cobalt 57, and 27, 27 plus one neutron. Okay, and that cobalt 57, its half life is the half. This is a radioactive molecule, so you have to calculate the lifetime of that radioactive molecule. It is 270 days. Okay, and then this cobalt 57 releasing the gamma ray. Oh, sorry, this cobalt 57 capture one electron from surroundings, electron capture, and it produced my iron. This electron captured to the nucleus, not at the peripheral of the nucleus, where the electron actually cloud found in the orbitals. This is not the orbital electron. We are talking about the nucleus at that nucleus it's capturing the electrons. So it will produce 57 here, 57 it will be becomes my 26, and it's I equals to 5 by 2, and this cobalt 57 it's uh, I equals to 7 by 2. Okay, as it is capture one electron it becomes its I value changes. This will release the gamma ray, high energy ray gamma ray, and the energy is nearly around 122 kilo electron volt, whereas my it will produce another 57 26 per I equals to 3 by 2, and this system actually releasing another gamma ray. Its energy around 14.4 kilo electron volt. It will producing the iron 56, 57, sorry, iron 57 with 26 I value equals to half. And this gamma ray actually, sorry, this gamma ray actually my source of gamma ray. Okay, then there we are talked about the Doppler effect. What is that Doppler effect? Actually gone through with that. As this is a high energetic light source coming from a particle like iron atom, it actually produce a backfire kind of thing, and just like a gun we are producing high energetic bullet from a gun, and that gun actually backfire to backwards direction, and which is actually required over here also is a very high energetic gamma ray which is coming from a, let's suppose, one particular atom, and that will actually back push the system to get that much of energy to come forward. So that is called the Doppler effect. And to minimize that, there is a one kind of loss of energy. To minimize that energy we are actually providing some energy or taking out of the energy to match the energy gap of the sample also have the same issue. If we hitting some high energetic particle, like this is a wave, gamma ray is a wave but it has a particle nature. Let's suppose it's hitting to a very high energetic wave is coming and hitting to my particular atom, it actually go forward, and it will also you will lose some energy, and in that case we actually miss some energy for this energy gap between the I equals to half to I equals to 3 by 2 does not match with our source energy. So for that we actually fixed the sample with a solid matrix, and also to minimize the Doppler effect we also fix the source in a solid matrix so that they cannot move to each other, cannot move simultaneously. And in that case sometimes we have some electron distribution or molecular property, something like that. My nucleus state is different than my source. Let's suppose we have a standard source. Let's suppose we have a metal iron coming from the metal iron, iron 57 is the metal iron. But in the complex, my my energy, my in a complex, my energy gap between the I equals to half to I equals to 3 by 2 is different. In that case, we have to properly align the energy gap between two source and the my sample. Otherwise, it cannot absorb any light. So to provide some energy or taking out of the energy from the gamma ray, we are actually moving the source, that is called Doppler velocity, by providing some velocity into that or taking out backward direction, that is the negative velocity we are talking about. And then we are properly aligning the energy what are required for the absorb of the gamma ray by the samples. Okay, and then we talked about the what is that, which orbital electronic configuration, electronic distribution, s orbital electrons are the major electron only are only interact with the nucleus. And then we talk about the radial distribution function of each and every each and every orbitals. Let's suppose 1s, 2s, 2p, and 3s, 3p, 3d. So for the 1s orbital, we have a psi square value over here, psi 0 square we are talking about, and we have a, this is the distance r from the nucleus. The This is the distribution, here a non-zero value and followed by decay. This is the 1s. How will be my 2s and 2p? We have 2s, there is a one node over here, radial distribution, something like this. This psi 0 square is the r, is 2s, and 2p will be something like from starting from the 0 to, okay, this will be 2p, and there is a 0 electron density at the nucleus, but in the s orbital we have a electron density at the nucleus. Although the probability of the electron density is measured over here, but there is a something non-zero electron density at the nucleus. So they have a effect. They can have a one effect at the nucleus if electron distribution is different for a different particular complex. So for the iron, that's why we are getting the different mass spectroscopy for each particular complex for the complex for iron. Similarly, for 3d orbital, similarly for 3 orbital, 3s, 3p, and 3d, we have it. Okay, no, no, no. This will be non-zero value. Start from here. Okay, the r psi square, psi 0 square, and my 3p will be, oh no, no, 3p will be another node over here. 3p and 3d, by the way, something like this. 3d. Okay, and so only, and we understand that only the s electron are the responsible for the nuclear electron interaction between nucleus and the electron. So because of the radial distribution says that this is the only s orbital has the non-zero value of the electrons at the nucleus. Okay, and then we move forward to talk about some delta value, that is that actually uh, how much my velocity, how much my delta velocity is required to to match my samples energy gap from the source. To calculate that, we actually have a some equation, that is we'll have is delta equals to 4 by 5 pi square, pi sorry, pi z square, 4 by 5 pi z square r square delta r by r, and followed by psi 0 square, psi 0 square of sample minus psi 0 square of source. Okay, and this is always depends on the electronic distribution of the my samples, electronic distribution of iron. Okay, and here is the delta r. Delta r equals to r of radius of nucleus. This is the radius of nucleus. R of excited state minus r of ground state. This is negative in iron 57 because of excited state radius, nuclear radius is lesser than the ground state nuclear radius. So this value is the negative value, and then we have a del r square value and the z square. So here only depends on the my electronic distribution is major factor at the nucleus. Okay, and then if we move forward, then we can find for the iron we have a electronic configuration something like Fe 5726. The electronic configuration we are right now we have to only talk about the nucleus electrons. We'll come back again and talk about the nucleus, where the electronic distribution, how electronic distribution is a major factor is playing a crucial role over here. Iron 57, we have electronic distribution something 1s2, 2s2, 2p6, 3s2, 3p6, and my 3d8 in complex complex form. Okay, so we only talked about the s orbital only. S orbital are responsible for the interaction for interaction. Okay, now what are the my s orbital? Okay, what are my s orbital? It is the 1s2, 2s2, and my 3s2. So we have the when the electronic configuration changes. Let's suppose we have an iron 3, iron 2, iron 1, or iron 0. Or we are where my electronic configuration changes only at the d orbital. So electronic distribution changes. Electron distribution changes 3d orbital only. Okay, so from here we have a effect. What is the effect we found in the orbitals, other s orbitals? Okay, to that we have to check that. Let's suppose once again we can write a electric distribution, radial distribution of the 3d and the 3s. We have a non-zero value over here for the s orbital and followed by, oh, okay, and then we have starting from the nucleus 0 to, can write it in a different color. We use initially green. Let's suppose we start with the green. This is my 3d orbital. Okay, so it is a 3s orbital and 3d orbital. In that 3s orbital, we have a electron density over here, and also 3d orbital we have a some distribution over here, which has a electron density over here. If my electronic distribution changes in a 3d orbital, so there are also some certain changes over here you can find in this region. So we can put it in a black color. In that region, we have a some electronic distribution also change when the 3d orbital changes, and that also affects that my 3s orbital's electron density. If there is a huge electron density over here, let's suppose 3d orbital has a d8 system, d8 electron, so it also less penetrate. It has a 3d orbital. It also interact with the electrons as close to the nucleus, not at the nucleus, at close to the nucleus. In that case, the s orbital shielding effect is will be the less, and then my electron, this the nuclear attraction of the s orbital will be the less. In that case, we have a higher d electron density. The shielding effect of my s orbital will be the max minimum. Okay, so these are the, so this is my s orbital. It will have the maximum effect for onto the nucleus. It has a minimum effect. Okay, now this region near to the nucleus, the interaction, this common region is a near to the nucleus. If some electron density changes in the 3D orbitals, we are saying once again, say it is a common region. If there is a huge electron density on d orbital, that will interact, that's attract, that will interact with the nucleus more, and in that case, s electron, if is s electron orbitals interaction will be less. Okay, so you can have this common region. In this common region has closer close affinity to the nucleus, and more is the d electron density, less will be the s orbital interaction. So in that case, what we will find? We will find something Mossbauer spectra, something like this. We have a, this is called Doppler velocity, millimeter per second. We'll have the transmissions, percentage of transmittance. Let's suppose it is 100%, and then it's sometimes we'll get, it's supposed to come something like this, but we'll get something like or this is my 0 0, here will be the positive, here will be the negative, plus positive. Okay, that means, it means actually my have a, this is my energy which initially may, I suppose this is the thing, energy gap we are talking about, and sometimes energy gap something like here to here, half I equals to half, 2 equals to 3 by 2, or in the lower case, when we are providing lower in energy, that means we have a closer energy gap, that is here, this one, where E sample greater than E source, where E sample less than E source. It's negative. Whenever we are getting the negative velocity, if you here we require the positive velocity. Okay, and this will be my E sample. So that means if we have higher electron density into the d orbital, then the splitting of this energy gap as my s orbital interaction will be the less, the higher the d electron density, higher lesser the s electron density, and then my delta value, where this is the delta value, this delta value, this term actually play a crucial role. But this is less interaction, and this will be my negative value. So this is a lower value, and this is the negative value. That means it is lesser negative value. So that means my the higher is the electron density, higher is the electron density, lesser will be the my negative value. So major point is that higher d electron density, less will be delta negative, less negative delta, less negative delta value. Clear? Means we have a higher electron density in d orbital. It's it shows some shielding effect on the 3s orbital, and 3s orbital will less interact with the nucleus. If less interact, then my psi square 0 ground state of for my sample will be my lower value. Okay. If it is lower value, my initial term is the negative, then it will be my less negative value, and then the total delta value will be the my less negative. For on other hand, we have a delta, we have a less electron density. That means let's suppose iron 2 and iron 3 both are the similar. Let's suppose iron ferricyanide and ferrocyanide, all the surroundings are similar, but one is the iron center is the plus 3 state, and another is the iron center is minus 3 state. In that case, if you see, then d electron density one times you will get the d5 system and d6 system. In the d5 system we have a less electron, d electron over there, so there is a chances of the high shielding in interaction of the s orbital at the nucleus will be higher than the my iron 2 system. In that situation, my psi square value will be high, and initial value is the negative. So negative higher value. That means iron 2 will have a negative high value of negative high value at the delta value, negative high delta value. Sorry. Okay. So for the, we can say over here we can write for the same ligand. Let's suppose we have a same ligand, same everything, only changes is the iron oxidation state changes. So for that one, for on a rough purposes we can say we have, this is the whole velocity millimeter per second, we have it percentage of transmittance. So for iron 3 will get more negative delta value, or for iron 2, okay, this is my Fe3 plus, and This will be for iron 2. This is Fe2 plus. Okay, so the lower oxidation state at will be the my more positive side, and lower oxidation side should be a less negative, less positive side. That means we can say vice versa. It will lower oxidation state. I'll show you one example over here, and this will be a higher oxidation state. Okay. Now comes into another things is the spin state. How it depends on the spin state. So a spin state. Okay. We have a two complex. One is the high spin complex, another is the low spin complex. Sometimes it changes the high spin to low spin to high spin. It always happens in with respect to the temperature. We have a strong field ligand for the low spin. We need a strong field ligand, strong field ligand, the high spin, high spin state. We need the weak field ligand. Strong field ligand generally my sigma donor and pi acceptor. These are generally sigma donor, pi donor, or sigma donor, parallelly pi donor, sigma donor, and only sigma donor. Okay, so for that, it's actually pull out for the strong field ligand, pull out the electron density from the d orbital. So here we can say here d electron density will be less. Shielding effect will be the more, shielding effect for the s orbital will be more, less shielding effect on the s orbital, and it will be generally d electron density increases as sigma donor, pi donor, or only sigma donor. So electron density. So d electron density. D electron density increases. Okay, and lesser will be my, oh, okay, higher will be my DCA S shielding effect. Higher S shielding effect, and then will less negative less negative delta value, and here we will get more negative delta value. Okay, how? If it pull out the d electron density from the system, it's similar to that my previous one, iron 3 and iron 2. Iron 2 have a less d electron density, it will have a less shielding effect on the s orbital, so s orbital contribution will be really high, and my initial r value or delta r value is the negative, so that means it will be at appears at the higher negative value, the higher negative delta value. And on other hand, the high spin complex here generally made of my sigma donor, pi donor, or only sigma donor. In that case, my sigma electron density, d electron density actually increases. It is sharing, and then in that case, the my s orbital shielding will be high, and interaction of the s orbital will be less to the nucleus. In that case, my size zero square value will be minimum lower, and then the negative lower value will get, here we will get in the high low spin complex we will uh, higher negative value, and high spin complex will get lower negative value. That means high spin complex will appear at the relatively more positive direction than my low spin one. So here also we will get a spectra something like, I can draw it over here. We have, okay, so this will be my, this will be, okay, this is the high spin one, this will be low spin. Okay, this is the low spin, this and other side is the high spin. Okay, now another factor comes into the picture. The one of the major factor will come right now. Sometimes, if we record the Mossbauer spectroscopy, we will get two lines. Let's suppose we have a ferricyanide. That means iron is the iron 3. So here its delta value will be the near to the more negative direction. And then that line actually split it into two line. Why is this happening so? It's supposed to come a one line, but it doesn't. But when we will take the ferrocyanide, that is iron 2, and that is a ferrocyanide molecule, will get only one line. Why this is happening so? Why this region actually comes into the picture? Now another factor is comes. I think you guys are aware of these things. This is the quadruple effect, nuclear quadruple effect. Okay, so how is this works? We have a, so we have a nucleus over here. Let's suppose we have a nucleus. If it is monopole, The electron density surrounding it. The nucleus is a spherical nucleus. In that case, this is the monopole we are talking about. When we'll get I equals to 0 or half. But where you can say the all the if it is spherical, the all the charge distribution at the nucleus will be similar. So here charge distribution is homogeneous. Now if I greater than half, what will happen? In that case, the nucleus charge distribution nucleus is not spherical. Nucleus is not spherical in that case. So in that case, it should be like this. It's not the spherical one, and there is surrounding electron density over here. Okay, so it implies that we have a nucleus where is that here is the more positive charges, here also more positive charges, and here less positive charges, which can implies my system something like here is the positive, here is the positive, here is negative, negative, because of comparing. Only the all are the positive charged, but less positive charge, more positive charge. So with respect to a certain reference, we can say in that it is a negative and it is the positive charge. Okay, this is called quadruple, and it has a some effect coming into that. So for this quadruple moment, we have a some mathematical term called del EQ, quadruple moment equals to minus mu2 plus infinity over space EQ rho. This is the charge of the nucleus. This is the charge density of the nucleus. R square 3 cos square theta minus 1 dV overall volume. This is the R and theta is the spherical coordinates, and rho, this is the charge of nucleus. This is the charge density. City of the nucleus. Okay, this is the equation. Now, if in non-spherical nucleus, if we place the non-spherical nucleus into the some electric field gradient system, so what will happen? We don't know. Now we can discuss about that. So we have a effect of the non-spherical nucleus onto the heterogeneous electric field. So we have electric field gradient. Electric field gradient called EFG. Okay. In that case, let's suppose we have a homogeneous electric field over here, and we place the spherical distribution. So overall quadruple moment, effective quadruple moment will be EQ equals to 0, EFG equals to 0. As it is spherical, if you put any electric field, there will be 0 value. And then if we have a homogeneous electron density, we have a different I equals to, let's suppose, non-spherical nucleus we place in a homogeneous condition. It will also face same effect. That means EQ will be not 0, but EFG will be 0. For that case, my quadruple moment delta EQ will be my 0. Okay. Now, another is that if we place spherical nucleus, electrically charge distribution, spherical nucleus into a heterogeneous system, hetero EFG fed by hetero electric field gradient is the heterogeneous, not the homogeneous case. In that case, it is spherical, so my EQ will be 0 and EFG will be my non-zero. But overall case will get 0. Now another opposite case, let's suppose we have a over here. Okay, we have a hetero nucleus, a hetero electric field gradient EFG. So EFG not equals to 0 and my EQ also not equals to 0. So in that case, we will have some defined state. We will also get a two defined state. For that, we can say here also we have a, this is the energy, let's suppose, and we have a initial one is the I equals to 3 by 2, I equals to half. If we place it, we have a my electric field gradient. That means we have a different ligand field as around the my atoms, my iron atoms. So electric field gradient will be there, and for the ground state we have the I equals to half, and this is the spherical one, spherical nucleus. You don't have any delta IQ value, quadruple moment value, quadruple moment. What is that? Quadruple moment effect for that case. So, but in that case, where EFG equals to 0, now my EFG not equals to 0. How it looks like? My here also here I equals to half because of here EFG not equals to 0. Now as it is spherical, ground state spherical. Now the excited state I equals to 3 by 2. It is not the spherical. So it's split into two parts. And right over here 3 by 2. So it's split into two parts, plus minus 3 by 2 plus minus half. So here generates the two different state. One is that I equals to plus minus 3 by 2 to, and here also another distribution. So if we have some quadruple moment into the nucleus, we will get two lines because of these two 3 by 2 excited states split into two different states. One is the plus 3 by 2, another is the minus plus minus 3 by 2, another is the plus minus half. So for that, so we can, in that case we'll get only this spectra. Oh, I can write it properly in the middle. The percentage of transmittance, this one, and this one my velocity millimeter per second, and it will looks like there one line over here, another line over here, and it's supposed to be similar. The middle point will be exactly similar to this point. If this value, this value. So average of this will be my delta value. This will be my delta value, and this is called delta EQ value. Quad. Sorry. This is called delta value, and this is called delta EQ value. Okay. Whenever we have a quadruple moment, then we'll get the two Mossbauer line. Okay, that's all. That is the major fundamental. So for the when my EFG, now question will be how my EFG will be 0 or non-zero. It also depends on the my coordination geometry and the lattice parameter. So condition for EFG 0 or non-zero. For that we have two parameter. One is that lattice parameter, lattice contribution. That means my coordination geometry. Another is the my valence contribution. That is my electronic distribution. The orbitals. Okay. Now one example. Iron 2 F6 2 plus. Okay. Fluoride. Iron fluoride 6 or FeCl6 3 minus ferrous chloride. Let's take a ferrous chloride compound. FeCl6 to 4 minus. That means iron is my iron 2 state. So my Fe over here, take a black iron, Cl, 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 and we have Cl over here, Cl here, Cl here, Cl minus quick field ligand. Initially it should be all the Cl is similar, so it's spherically oriented or octahedrally coordinated, so it's all the direction Cl is the similar, so that means initially we can guess this will be my lattice contribution should be is 0, but will not get the 0 lattice contribution. Now there is another question coming to picture during the electronic distribution. So weak field ligand, that means it will be my low spin, a high spin system. Okay, so electronic distribution will be like T2G and EG. We have the 6 electrons, all the field high spin as it is high spin. My T2G6, T2G no, T2G4 and EG2. Okay, T2G4, EG6. So as it is, so it will show Jonteller distortion. So as one orbital occupied two electrons in a one direction, it will show the Jonteller distortion. That is my electron should be comes into like this way. This is the easy level splitted into this way, and my okay, this will be my T2G easy. So it will show some Z in distortion. Ready? Yes, Z of distortion. And then this will be my lattice, this bond will be go out longer. This Cl will longer and it will becomes lattice contribution. Lattice contribution will be there. Second is this is not the homogeneous electron distribution. If T2G6 is will be the homogeneous contribution, T2G3 is the homogeneous distribution, or T2G6 is Eg2 will be the will not the homogeneous distribution. So this is the inhomogeneous electron distribution. So balanced contribution will be there. Balance contribution. This is also positive. So then we'll get the spectra like percentage of transmittance, the velocity, millimeter per second, and the Mossbauer spectra like this. And this middle point will be my delta value. This is the delta value 1.2. millimeter per second, and this will be my 1.0 sorry minus 0.5 millimeter per second. This one will be 2.9 millimeter. Oh no, this is for the water. Do it have some value? I don't remember for the water. For if similar like is 2 whole 6 2 plus, in that case we will get this delta value will be 1.2 millimeter per second, and this delta EQ value is 3.4 millimeter per second. Okay, now another example we talked about initially, that is my cobalt hexacyanoferrous. So this cobalt, sorry, iron, sorry, not cobalt. There will be no cobalt, only iron we are talking about. Cn whole 6 4 minus. Okay, it is D6 system. D6. All the coordination site should be Fe, Cn, 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 and this will be my Cn. So in that case, similarly, we have a lattice contribution. Contribution is to 0. Now, electron distribution, how will be my electron distribution? As Cn is a strong field ligand, we have a T2G level field of T2G6 is 0. So, as T2G6, in the all direction we have a similar electron density. That means it is homogeneous electron distribution. So, valence distribution will be valence contribution equals to 0. We'll give, so overall delta EQ will be my 0. So we'll get only one line. Yes, for the iron ferrous hexacyanoferrous, this is 4 minus. We'll get only one line. So next, let's suppose we're supposed to change the slide. Okay, so where I was, how will be my Mossbauer spectra? Okay, so my Mossbauer spectra looks like per velocity millimeter per second, we have percentage of transmittance. The spectra is 1 line. And this delta value is minus 0.13 millimeter per second. Okay, previously we have a delta value of plus 1.2 millimeter per second. Now we have a delta value of minus 0.13 millimeter per second. As we change the spin state, as we initially said that if we change the spin state, if it is high spin system, then it will comes in a more positive direction. If it is low spin system, then it will be comes into the more negative direction. So here also you can say similar effect over here. We have a cobalt iron hexacyanide iron 2 hexacyano iron 2. We have a low spin system, then the delta value is the more negative, that is minus 0.13. On other hand, the hexa aqua iron 2, it is actually showing a delta value of plus 0. Or plus 1.2 millimeter per second. So that means we have a higher delta value over there. Okay, so that's picture actually comes into that. We have a speed different spin state, we have a different nuclei, then we will have a different delta value we talked about initially. So high spin system will comes into higher more less negative direction, and low spin system will comes into more negative direction. On other hand, another example, interesting example, on other hand, this iron 3 hexacyano, another oxidation, there's iron 3 Cn whole 6 3 minus. For that one, we have a electron distribution over here. How will be? My electron distribution will be T2G AG 1 2 3 5 5. It's supposed to come that way, but here we'll get John Taylor's distortion. John Taylor's distortion, and we will find this is energy distribution. J dot distortion. Initially here will be lattice contribution active, lattice contribution, and then we have valence contribution. So we'll get the spectra something like so. If we middle of that, my delta value, that is the value is the minus 0.03 millimeter per second. Now here is the minus 0.13, here is the minus 0.03. This is the iron 2 plus this is the iron 3. Is supposed to the iron 2 will supposed to come at the more positive direction, but it becomes the reverse. So why this is happen? Because of the both experiment has been done in a different temperature. So if you want to check one parameter, we supposed to keep constant all other parameter into of your experiment. So you cannot change the both the parameters simultaneously and want to check there if there is any effect or not. So if it is iron 2, it's supposed to come at a minus more iron 2 less my negative direction, but it will observing that this is the more negative direction than the iron 3. Because of that, it has been recorded in a different temperature iron 2 for the iron hexacyan of ferret, or these two experiment has been done in a different temperature. And in that temperature, actually iron 3, where the my iron hexacyan of ferrous is been recorded, in that case delta value around my around minus 0.5 millimeter per second. It's supposed to, it comes at that temperature. Okay, so then we have a one another interesting one. So we can show it once. Time to ahead. Okay, we have another example for this is FeCN whole 5 n. So how it looks like? If you were here, CN, nitrosyl group, CN group. So here the ligand distribution is different. So here we active the lattice pair. That is contribution. Now is the valence contribution. We are saying it's not because of that the cyanide and the nitrosyl group both are the very strong field ligand. It has a D6 system. So iron 2, this is the iron 2. Okay, D6 system we have a T2G6 is A0. So where valence distribution, symmetric distribution is there, so valence contribution will be my 0, and then only contribution is the lattice contribution. So here also we get delta EQ equals to non-zero. So in that case, the delta value has been found minus 0.27 millimeter per second. And my delta EQ value was to 1.85 millimeter per second. Okay, so now question is for the iron CN whole 6 4 minus, it has a delta value around minus 0.13 millimeter per second. The temperature are constant, both the case, for both case. So that means the delta value of the hexacyanopherus is minus 0.13, but one cyanide is usually replaced by the nitrosyl group, the delta value is the minus 0.27. That means more negative. It means around more negative, around minus 0.114 millimeter per second more negative. That means this nitrosyl group has a higher electron pulling effect than my cyanide. So nitrosyl group is a much more electron pulling effect, has a much more electron pulling effect than the cyanide, and it is a very strong pi acceptance ligand than the cyanide. Okay, so nitrosyl is a very strong electron withdrawing group over here. That actually reflects in that delta value. Okay, now we have another interesting Okay, this is the iron chlorine complex. Chlorine complex. So this is the iron center, which is similar to the porphyrin system. So they and this group actually monitoring the CO2 reduction by using this chlorine complex, this iron complex, P complex. Okay, they want to trap some intermediate where this my system usually formed. It is in high spin or low spin system actually going through. They are looking for that. So they took iron 2 chlorine system. Okay, this is the iron 2. They started with the electron, iron 3. They takes one electron. This iron 2 they are getting. This iron 2 and iron 1 they are getting from a different potential, and they try to monitor where my CO2 actually bound and how the this intermediate actually going through with this catalysis happens. They are trying to monitor the mechanism. Okay, so they got this iron 2 system. This is Mossbauer active T6 system. So in that case, they got the experimental data over here. This is this dot point are mainly the experimental data, and that has been actually uh, simulate deconvolute this data by either some software they are using, and then deconvolute the data how much their mm, data has been found. Okay, so they started they record the intermediate over here. This one they got the dot one is the actual data, and this dash red on is the fitted data. And then they found this intermediate actually found this intermediate one, this one is the intermediate, this is the iron 3. So iron 3 will be the more at will be more negative direction. So here you can say it's around more negative direction than the my iron 2. This is we are talking about the iron 2 here. This is the iron 2 spectrum. Iron 2 CO2 bound. Iron 2 CO2 bound spectra, which is around more positive direction. So they deconvolute, they found that there is a iron 3 over here and some iron 2 residual confined with that spectra. They deconvolute it, how much iron 2 is there, they have been recorded. And on the other hand, they again reduce the iron 3 to iron 1 by providing external electron source, and they record that there is a generation of the iron 2, and along with the residual iron 3, iron 2, which is actually found over here. This is the data they found. The iron 2 is at more the intermediate 2 at the more positive direction, and the intermediate 1 is the more negative direction. That means more negative direction, intermediate one is the cobalt 3 and the iron 3, sorry, iron 3, and the more positive direction delta value is the iron 2. So here the hypothesis is the okay. They found that the iron intermediate one, iron 3, is CO2 bound iron 3 they found, and after one electron reduction they found iron 2 CO2 bound, and they found this iron 2 and iron 3 has been recorded differently, and then they compare with those this iron 2 and this iron 2 both are different, which is actually found over here. This iron 2 here we are finding this iron 2, initial iron 2, and CO2 by iron 2 split it, and it has a delta EQ value is high because of the another ligand is the CO2. On the other hand, on reverse side there is a solvent, and on top of that there is a CO2 solvent. So there will be some lattice contribution as well as the iron 3 iron 2, and it's showing a higher splitting value. So here on other hand, when we are talking about the iron 2, only iron 2 over here, this one has a, on upper hand there is a solvent, and there is a solvent less lattice contribution, so we'll get the splitting will be the less. So we can get this is the splitting over only the residual iron 2, and this is the splitting of intermediate delta AQ value. I have that paper, so I'll attach with that what is the number of DI number I can share with you. So I think here we can get, yes, this is the DI number. Copying that. Okay, this is the DI number. If you want to check, go through that with that publication, and then we'll get the this is the publication. Sorry, this publication will get that all the data parameters. What is the delta AQ value we will get, and the delta value will get. Okay. Oh, sir, sorry. To this, I'll stop over here, and next class, next day onwards, we'll get some more problem and try to solve all those problems as you require. Okay. So to summarize this, so to summarize the say all the parameters we talk about what is we talked about we talked about how the s electron shielding effect actually play a major factor to determine my characteristic of the iron center. Okay, so more will be the d electron density, high will be the shielding on the s orbital, inner s orbital, and then there will be a psi 0 square value will be my less psi 0 square value, and negative less psi 0 square value, and that will be at more positive direction. So that's why low spin and the higher oxidation iron system found in a the delta value found in more positive direction. On the other hand, lesser is the higher is the lesser is the d electron density, less shielding effect on the s orbital, inner s orbital. They will have a higher size square value and the nucleus, and the higher size square value, the overall delta value will be the higher negative direction. That means we'll get a higher oxidation system will get delta value will get at the more negative direction. And then we talked about some quadruple moment. So how the quadruple moment actually plays a crucial role to split my energy state. And then we'll, for if there is some quadruple moment present over here, this quadruple moment feels a different electronic field gradient onto the complex. If complex is homogeneous, homogeneously distributed all the ligand field, then it will, the EFG will be 0, and in that case we will get one spectra. On other hand, this will get a two line for iron system. And we get some example. One is the iron chloride, iron hexaaqua system. We'll offer the iron is the iron 2. It is a low spin system, and we'll get the electronic lattice distribution will be 0 because of lattice distribution will be there because of the John Taylor distortion. All the axial CL bond will be the different length. On other hand, balance distribution will be there because of the electronic distribution is driven different, and EFG will be non-zero. If both come together and we got the delta EQ value for the iron hexaqua iron 2, in that case delta value is in 1.2 millimeter per second and delta EQ value is 3.4 millimeter per second. On other hand, for the hexacyanoferrous, for that lattice contribution is 0 because of the it is homogeneously distributed all the cyanide on on the octahedral at the octahedral geometry. We'll get the delta EQ value equals to 0, and we'll get the only one line. And there only the delta value we got is minus 1.313 volt, not volt, millimeter per second. For iron 3 hexacyanoferric, for that we have a lattice contribution there because of the John Taylor distribution, and the valence distribution contribution will be there because of T2G5 system. So with T2G5 system, there is a heterogeneous electron distribution, but there will be non-zero EFG value, and then the spectra split it into two lines, and we got the delta value around delta EQ value around 0.5 millimeter per second, and and the and the delta value is minus 0.5 millimeter per second for that temperature. In that temperature, delta Fe hexacyanoferrous has been recorded. Okay, and then we have a nitrosyl group. If you have a present nitrosyl group over there, then we'll have some data for the delta. Depending on the delta value, we can say the nitrosyl higher as the delta value of the nitrosyl group replaced in here, the delta value is more negative. That means it has a strong pi acceptance effect than cyanide one. As a lower the it's lowering the electron density of d orbital. That means higher the s orbital contribution at the nucleus, and then it will actually give us the higher negative delta value. That's we found, and then we can say nitrosyl has a higher electron pulling effect than the cyanide. Okay, and then we gone through a one mechanism apart from the Professor Dey's group. They try to trap some intermediate during the catalysis, and they able to detect this iron 3 carbon dioxide bound system by the Mossbauer spectroscopy, and iron as well as the iron 2. And they also record some bare iron 2 system by the Mossbauer, and where we found the delta EQ value for the iron 2 bound system and free system is different. From that, we can say in that system we have a both iron 3 and the iron 2 CO2 bound system, as well as the iron 2 free system has been present into the system. Okay, to that I will stop over here. If you found any, if you found any queries or any problems during solving the assignments, please let me know anywhere by comment into my YouTube video or joining the class. Okay, thank you. To which to that I'm stop over here. Let's save the stop sharing. Done and leave the meeting. Okay.